Okay, folks, let's get going here. So I'm working off of two slide decks, both lecture 4 carryover from what we didn't finish last time, and then also lecture 5. So I just want to start out with some announcements from the lecture 5 slide deck, and then I'll jump back to 4. So just a couple of announcements for you. Where in the heck are my darn announcements here? Here we go. Okay, so just to remind you that Lab 1 is due on Sunday, a minute before midnight, and there is a Moodle uplink for submitting that. And I'd like you to submit two things. Submit a text file of your source code, and then take a screen capture of you using your code to, to interact with it. So just those two things. Okay, today's lecture is going to complete this crash course in C that we're doing. And I don't expect to get through all of the slides from packet lecture 4 and packet 5. There's an awful lot there. But whatever I don't cover, I do want you to go through and read it offline. And, I'm obviously showing you lots and lots of examples of code that I'd like you to, or encourage you to go ahead and try out some of them yourself. Get them to work, modify them so that you get the hang of this stuff. And you can do that either with a downloaded compiler or with that online GBD compiler that I've been introducing either, okay? Now, just to orient you, next week, what we're going to do is we're going to get into embedded programming. So we'll leave behind our laptops and all that. Well, we'll continue to use the laptop as the host computer for writing our code, but we'll be compiling things onto microcontrollers. And there is another tool chain that you do have to install for the embedded work. And there's a link there. That's courtesy of Professor Redikoff from University of Southern California. They have an embedded systems course out there. They structure the curriculum for ECE a little differently from the way we do, but they've got a nice tutorial on how to set up the tool chain. And the thing that's tricky about setting up the tool chain for what's to come, the Windows part is pretty straightforward. And the tool chain, that is the compiler and the set of tools that you need to take some C code, cross-compile it onto an AVR microcontroller, and then download the resulting code to a microcontroller. The set of tools, we call that the tool chain. And the open source stuff that's out there historically has been a 32-bit code. And that'll work fine on your Windows machine. Newer Macs insist on having 64-bit code. You may have run into this starting with, I think it started with Catalina. So if you tried to download something that wasn't a 64-bit app, the Mac would have a problem with it. So these folks out at USC have done a nice job figuring out a way around that, and that's why we're pointing to their URL, and we're in communication with them about this stuff. So this is just sort of heads up on this. You don't actually have to install this tool chain yet. If you're concentrating on the homework assignment and you want to get that done first, then you can start to worry about this on Monday after you've submitted the assignment, and I'll come back to this on Monday. Okay, so that was slide deck 4. Now I'm going to jump back to, that was slide deck 5. I'm going to jump back to slide deck 4 and pick it up where we left off. And we were talking about what we call control structures. Let me see, I may have a question here in the chat. Okay, so when we say control structures, you're controlling the execution, and instead of just going one statement, the next statement, the next statement, the next statement, the next statement, going in order, a control structure allows branching. And so we'll look at if statements, we'll look at if else statements, and we'll look at loops. And I expect that you've seen all of this before in Python or in another language. So this will be review, and it's really a matter of figuring out what's the syntax, or what's the syntax of these structures in C, and what are the things that are particular about doing this in C. So we'll just start out with the if statement, the if block, we call it. This is an example of a control structure. Okay, and so we'll just start out with the thing right up here. If some condition is true, then do this statement. Okay. Now, if all you have is one statement, right? If A is equal to 42, right? Then you want to print something. You could just have a print statement following the if and condition. More likely, after you test a condition, after your if statement, you want to do more than one thing. You want to have a block of code that follows, and so then you would surround your block of code by braces, by the curly braces. Now, C will allow you to skip those curly braces if you only have a single instruction that is going to follow your if condition. But most style guidelines recommend that you always use these curly braces, and I'll show you examples of this. And in terms of the curly braces, there are two different ways of formatting them. You can have the opening curly brace in line with the condition. See how this curly brace here is in line, or you can have those curly braces in the same column. The compiler doesn't care, the computer doesn't care, but it's for your eyes that you do this indenting and formatting. Most people would agree that when you indent things as shown on the left with these curly braces in a column, that's easier to read. But if you actually have the first curly brace in the same line as your if condition, that's more compact code. That's how I'm going to be showing it all the time. I do find it easier to read the way it's shown on the left, but I'm always trying to show you code, and I won't try to keep it to one page of code. And so to do that, I need to keep it compressed. How should you do it? It doesn't matter, but what you want to do is pick one of these styles and then stay with it. Stay with it, in one program. Don't change styles. And so just generally be consistent with it. Okay, so that's the if block. There's also the if else structure. Okay, if a condition is true, if something happens to be true, then do this block of code. Else, if that condition is not true, then do this block of code. Right, and the same thing applies to the way you do the curly braces. I mean, you have this first block of code, the stuff that's going to get done if the condition is code, you surround that by curly braces, and the stuff that's going to get done if the condition is not true, you also surround those by curly braces. Okay, and you can use either of those styles. Now, I'm going to back up a bit, and back up to slide 17 here. I'll show you some examples of this, but what I wanted to point out is something we talked about the other day here. A condition is considered to be true if the result of that condition is anything other than 0. The condition is false if the result of the condition is 0. And so I was asked at the end of class today, why did the designers of C choose to do it this way? Why didn't they just say 0 is false and 1 is true, instead of 0 is false and anything non-zero is true? And I don't know the answer to that. I'm not familiar enough with the motivations and the hows and whys of why they architected C this way. But it is how C is implemented, and I'll show you some of the implications of it. Okay, so here's we're on slide 9, simple code here. And this is using this online GDB IDE. Okay, what is this code doing? So first, I'm just prompting the user to enter an int. Okay, and then I'm just testing if so the user is going to enter an int, a number. but it's an int. So it could be positive, it could be negative, it could be 0, but it's any int. Okay, and then look at the way I'm doing the if-else block. I'm just testing the value of that input. So if user input, I'm not asking if user input equals 4 or if user input is greater than or less than. I could do those things, but I'm just using that input value itself as the condition. Okay, and what we'll see is if that input is anything other than 0, then we will end up evaluating this. And if that input is 0, we'll end up evaluating the else block. Okay, and so when I run it the first time, please enter an int. I typed in a 0 and it says, okay, 0 is false. So it's printing out that number and 0 is false. Now I'll go to do it again. I entered the number 1, 2, 3, 4, 5, 6, and it says that is true. And then I did it again, and I actually typed minus 99.012, and it said minus 99 is true. Now you could run into trouble with something like this. Here, the scanf is looking for an int, right? This format specifier, we went through this briefly the other day, but that specifies an int, and user input is an int, and you can see that I've typed a float. What would happen is only the minus 99 gets read into the int. The other part, the 0.012, is there in an input buffer. If you had another scanf statement later on, it would have to contend with that 0.012. If we were learning C and we were going to be doing a lot of work with the terminal, with keyboards and monitors, we'd spend a lot of time on scanf and how to prevent this from creating problems when the user types in something that's different from the specified format. But as I've said before, these embedded things that we're working on typically don't have keyboards, so we're not going to be spending a lot of time on that. Okay, just one. The only difference between here, slide 22, and the previous one is I just changed the way I formatted this, to make it look pretty. So here you see I have my curly braces in a column, and then when I go to the next slide here, I've just changed those. So I have the opening curly brace here. Okay, and so you can see it's more compressed, right? It doesn't take up as much space. I'm going to flip back and forth, all right? So I'm going to go back and forth, back and forth. And you can decide for yourself which one is easier for you to read and understand. This gets important when you have multiple if statements. You have if. Well, I'm going to show you the if-else in just a minute, the if-else if. And when you have a lot of different structures like this, it's really important to be able to follow the line of these curly braces. So that's just a bit of programming style, okay? All right.
There's a question in the chat.
Go ahead.
In the chat, so if you don't type an int, it will be false, correct? That's in the chat.
So I'm not getting the chat on my screen here, but repeat that. So repeat. Let's see. I've got to figure out why I'm not getting the chat here. Yeah, the question was that anything other than 0 is going to be true. Right. I think that was the question.
Okay.
Okay. All right. Now. Okay, so for whatever reason, I'm having trouble seeing the chat when I'm projecting PowerPoint. So,
okay.
Okay.
I'll bring any relevant questions to your attention.
Yeah, very good. Thanks, David. All right. Okay. So just a variation on this. You've got the if statement, if else, right? And then there's if, else, if, else. Okay, and I think it's pretty self-explanatory what's going on. So let's look at, we have the condition. Let's get the pen back here, right? If condition 1 is true, we're going to execute this block of code. Else, if condition 2 is true, will execute this block of code. And you can keep that going. You can have multiple conditions. You can have if, else if, else if, else if, else if, and so forth. And then finally, if none of those are true, then this else block of code would be executed. You don't have to have that else. So the else if and the else, these are optional, but I'm just showing you the different variations of this structure. Okay, just an example of a piece of code here that utilizes some of this. So to look at the top, this is it's going to ask for the user's age, and it's going to print out their age in days and minutes. And it's also going to print out some age-related information. And by that, it's going to tell you based on your age, are you a baby boomer? Are you a Gen Z person? Are you, something else, right? It's these informal demographic cohort categories. And so I guess what I'm just going to do is I won't spend the time showing you the whole structure of this code. I'm just going to jump and show you this function down here. And all we're going to do is, based on someone's year of birth, we're going to print out what their informal demographic cohort is. We're using, let's see, let me just show you the output here, and then I'll sort of break it down. Okay, so it prompts me, please enter the year you were born. I typed in 1962. It says on your next birthday, your age will be 59 years, so many days or so many hours. And then it says you're a baby boomer. All right, that's me. Then I ran it again, typed in 2004. On your next birthday, your age will be 17 years and you're a Gen Z. Okay, then I did it again. I typed in age 1970 and it said, you're neither a boomer, a millennial, or a Gen Z. And I just wanted to come up with something, even though it's a little contrived, to just show you an example of an if-else block. And here's the if-else structure down here. That's done in a function. And what I did is I called the function and I gave it year of birth. And then the test is, if year of birth is greater than boomer low and year of birth is less than boomer high, then print you're a baby boomer, okay? Boomer low and boomer high, they're all capital letters. That means that those are all defined up in some preprocessor directives up top. And boomer low is just 1946 and boomer high is 1964. That was the age at which we decided we're going to call people baby boomers, right? And then so forth for millennials and Gen Z. So I just wanted to show you an example of a simple if, else block. Okay, that's the if statement using conditionals. Now let's look at loops. And I know you've seen loops before, so so think about this as a review. We just want to see how the syntax is done in C. So, well, there are three loops. There's a while loop, there's a do loop, and a for loop. And here's the while loop. While some condition is true, do everything in between the curly braces. And just keep looping as long as the condition remains true. So what happens is, you're executing the statements above the while loop. You get to while, it tests the condition, it does everything in the block, it tests the condition, does everything in this block, and it keeps doing that as long as that condition is true. Okay, here's an example down here. I start out by setting I equals 0, and then I say while I less than 10, go ahead and print this is iteration, and it would print this is iteration number 1. Then here I have I equal I plus 1. This is shorthand for I equal I plus 1. So the next time through, I is 2, and then I is 3, I is 4, I is 5, and it'll keep on looping. And as long as I is less than 10, we stay in the loop. Okay. Something that's a little, what's notable, something that we're going to see all the time in embedded systems. So just imagine this, this example that I just showed you, but suppose that I don't have this. What would happen if I take out the I plus plus, right? That's not there. So our while loop is, we start out, we initialize I equals 0, and then we say while I is less than 10, print something, right? And then we're back up to testing while I less than 10. I never changes, so I is always less than 10. So we would be in that loop forever, right? Until you caused control to stop. That would be Control C on your if you're running this at your console. If you were running this on a microcontroller and you actually the way we program microcontrollers is usually to be in an infinite loop. They're just executing the same thing over and over and over again, day and night. And so that'll make more sense to you on Monday. We'll start that. But I just want to show you this one line of code down here. This is, if you have a statement like this, while 1, and then the block of code is just a semicolon. So 1 is always true, right? So while, you know, the condition would be true, you're going to execute the contents in between the curly braces. It's just the null statement. So it doesn't do anything. It just waits. So this would be, you'd be an infinite loop and you'd just be sitting there waiting. Nothing would happen. The whole thing would hang. Okay. And we'll see variations on that when we're doing our embedded stuff. Okay. Here's an example.
Question in the chat.
Okay.
Does a loop need a return statement?
A loop doesn't need a return statement. A return statement is for the end of a function, and so you'll have a return statement at the end of main and at the end of your various functions. But you wouldn't. I mean, you could, if you chose to, put a return statement in a loop, and you would then exit from the function as soon as you reached it. But it's not the normal circumstance. There may be certain conditions in a loop where you want to, if something happens while you're in a loop, you want to exit from your function. You could do that, but it's not the usual structure. I'm going to show you in a little bit, 2 different commands, break and continue, which are ways of exiting out of a loop based on different conditions. Okay, someone asked, if you don't type an int, it will be false. No, that's not actually true. Let's see. In this particular code, maybe you're referring to this one. Yeah, in this particular code, the condition is while the user input is not equal to 0. So anything other than 0. And so let's go ahead and see what happens when I run it, right? First I type a 1, it says, it tells me you entered 1. Then I type in a 4, you entered 4. I type in -9, it says you entered 9. Then I type in a 0, it says you entered 0, and it stops. Because the condition here is I'm asking the user for them to enter an int. I'm printing it out, and I'm going to keep looping as long as that int is not equal to 0. Okay.
Professor, there's a question in the chat. What if you entered a letter instead of a number?
Let's see. I would expect in this case that scanf would fail if you and let's suppose the very first time through, I've defined user input to be 99 up here. So the first condition is going to be true. Then I ask the user to enter an int, and let's suppose I type the letter A. The variable user input would not change in that case. And so I would end up going up, back up again, and user input would still be 99 because the A that I typed in at the keyboard would not be entered into that variable. So I would persist with user input equal to 99. That would be a case where the scanf, it failed. It failed to take the user input and park it in the variable user input. Just as a bit of an aside, so scanf is a function, right? It's not one of the C keywords. It's a function in the C library, and when you call scanf, it's doing a couple things. Like when we call this, what it's doing is it's causing the users, assuming the user types in an int, no decimal point and no characters, that's going to get then stored in the memory location corresponding to user int. The function scanf also returns itself. It returns an int equal to the number of entries that were successful in the scanf operation. So if the user actually typed in an int correctly, scanf would return a 1. If the user typed in a character other than something other than an int, then scanf would return a 0. And so if we were doing this in a way that we wanted to really protect against the user typing in something inconsistent with our instructions, we would have to actually check the value of scanf. But as I said before, it's not something we're going to be doing because we're not going to spend a lot of time on keyboard input. Let's see. Don't scanners take the ASCII value of letters? Yes, you would take the ASCII value of the letter, but you would have to have used the format specifier C and entered the C would correspond to an ASCII character, whereas D corresponds to an int. Okay, let's just look at the do loop now. So very similar to the while loop, it's just sort of upside down a little bit, right? So you have do a block of code, and you're going to do that block of code while the condition is true. Okay, so the point about this one is first it will do the block of code, then it will do the test. Whereas the while loop does the test first, then it executes the block of code. Here we execute the block of code, then we do the test. A consequence of this is that a do loop will always run at least once. Okay, a do loop will always run at least once. Now, most of the things that you can implement with a do loop, you can also implement with a while loop. Here's just an example of that same program as before, but implemented as a do loop. And I won't spend the time to go through it line by line. But I do want to show you a mistake that many people make. This is a very easy mistake to make. And let's look at this code here. So suppose I have A equals 10. I would need to have a semicolon, and then B equal 20. Okay. And then I say, if A equal B, print they're equal, else print they're not equal. If you wrote this code, you would not get a compiler error. This would be valid code. And let's just go ahead and see what happens if we put this into a piece of code. So first, well, let's see. I'm on slide 35. What I'm going to do is I'm going to jump to slide 36. Then I'll come back to 35. So look at the way look at the code I've got. I have int A equal 10, int B equal 20. If A equal B, print these two are equal. Else print they're not equal, and then return. So I run it, right? And what happens? It shows me 20 and 20 are equal. Now what happened? I started out A equal 10, B equal 20. If A equal B, right? If A is 10 and B is 20, right? I'm expecting this to print, to show me that these are not equal. And the problem that we have here is over here, instead of using the test for equality, the double equals, I used the assignment operator, right? What I've done is I've got a statement here, A equals B. So instead of actually testing for equality, I took variable A and I assigned that the value of B, which is 20. So the expression A equals B, that expression evaluates to 20. 20 is non-zero, so this would always be true. So this is one of these kind of quirky, crazy things about C, that you can do this. And what C does is it assumes you know what you're doing, and it'll allow you to do it. The correct way to do this, I'll jump back to slide 35 here, right, is I have that equality operator here. the test for equality. If A is equal to B. And when I run this one, it shows us 10 and 20 are not equal. So just be aware of this. Many of you are going to do this. You're going to do this in a piece of code, and you're going to spend a lot of time trying to figure out what the heck did you do wrong. And it's because you use the assignment operator instead of the test for equality operator here. Okay, and it's an easy mistake to make. That's why I'm dwelling on it. Okay, the last of the loops is the for loop, and I believe you've seen for loops before. There are three pieces to it. There's the initialization, the condition, then the update, and then the block of code. Okay, and so here we have an example. For I equal 1, I less than 10, and then I equal I plus 1. So the first thing that happens, very first thing that happens is it sets I equal 1, and then it tests to see if I is less than 10. If so, it'll print this out. And when it's done doing that, it will go ahead and do the update. Then it'll test the condition, do the block of code, and then do the update. Okay, and once you've programmed this a couple of times, you'll get the hang of it. Common mistake: you have to have semicolons here, not commas. And if you have commas, you'll get a compiler error. But that's a common mistake here. Okay, here's a piece of code that just averages some numbers, and I have a number of things going on in this code, so I'll walk you through it. Let's just look at the output here.
The chat question resolved itself.
Okay, so what we're going to do is we're going to take an average of a bunch of ints that the user inputs. Then we're asking the user, how many ints would you like to average? Okay, so here, how many ints would you like to average? 5. It says, okay, enter value number 1, 2, 3, 4, and 5. Okay, you've done that. Here's the average. It's 0.2. So far, so good. So this is a classic example of a code that's implemented with a for loop. And how are we doing an average? What I've got is a value called accumulate, and I'm going to ask the user, for input number 1, number 2, number 3, number 4, number 5. I'm going to add those to this variable called accumulate, and then when I'm done, I'll divide accumulate by the number of ints that were entered. Okay, so my variables are n is the number of ints that the user wants to average. Okay, and here we ask the user, how many ints would you like to average? And then we enter that into n, and then we're looping. I goes from 1, I less than or equal to n, right? And once we get in here, we're saying, okay, give me value number I is the index of this loop. We enter that in, we accumulate all those values, and then when we're done, we compute the average. And notice the way I'm computing the average. We're dealing with ints here. Right, all of my variables are ints. They didn't have to be. I could have used floats, but I made them all ints. So you have to be careful when you want to compute an average with ints. So what I'm doing is an explicit type conversion. Right, when I specify float in parentheses before accumulate, it will temporarily convert that to a float. Then it'll divide by n, and that's how it can properly give us the average. Okay. So simple piece of code. Now, suppose that we wanted to modify the code. Instead of asking the user, tell me beforehand how many you want to average, suppose we did it a different way. What we want to do is, I'm going to allow the user to keep entering numbers until they enter 0, and then I'm going to give them the average. So let's take a look at the result down here, okay? I say enter the number and enter 0 to quit. So I type in 10, 11, 13, and then 0. It says, okay, the average of the 3 values is 11.33. So this is a case where we use a while loop, and I'm using a statement that you haven't yet seen before called break. And I'm using that to break out of the while loop. Okay, so that's why the title of this slide is breaking out of the while loop. And so here what's happening is within the while loop here, Okay, I'm asking the user enter a number, and I'm giving the user the instruction enter a 0 to quit. We're scanf, we're getting the user's value, storing it in the variable value. Then I check to see if that's equal to 0. If it is, then we break. And what break does is it will execute out of the loop, and it'll start down here. So the statement break is used to break out of a loop. Okay, so that's a statement that you'll use sometimes. There's another variation of that where break breaks out of a loop. There's also continue, and what continue will do is it won't break out of the loop, but it'll skip the rest of the loop. What I mean by that is, let's look at this example. Okay, so here's one where I'm going to allow the user to keep entering numbers until they specify a 0. And if they enter a negative number, I'm going to ignore it. So let's look at the run over here. So enter a number and I tell the user enter 0 to quit. They put in a 1, a 2, a 3, and then a -4, which we're going to ignore. Then they type in a 0, and we say, okay, the average of the 3 values is 2. So it ignored the negative number, and it stopped taking inputs at the 0. And what I've got here is that same break statement as we had before, but I also have this check here. If the user input a number less than 0, continue. And what continue will do is it will go back up to the top of the while loop. So break exits from the while loop. What continue does is it stops executing the blocks within the loop, and it goes back up to the top of it again. So break and continue. All right, and so I wanted you just to see those at this point. Here, I'm back to the list of C keywords. We haven't actually seen case, so this should be black. We haven't seen case yet, but all the rest we've touched ever so quickly. We've seen those. The ones in black are the ones we haven't yet seen. Everything else we've seen and seen some examples of in this crash course. Okay, what I'm going to do now is switch to slide deck number 5. And we'll continue the death by PowerPoint, right? Okay, so we're going to talk about, well, let me, so I already showed you this announcement slide. So this, what I call a crash course in C, it started out with lecture 2, where we looked just briefly at the structure of a C program. I gave you an example of a code. I said, don't worry about all the curly braces, just try to get a sense of what it looks like. And we did hello world. Then we talked about data types, where we introduced int, float, double, and char, right? And so we spent some time on those. And that stuff's obviously a big deal in C, right? You didn't have to worry about that stuff when you were doing things in Python, but it's a big deal in C. Why is that? Well, C is a language that is used for systems programming, where you have to get down and dirty with the microprocessor, and you have to know what's happening in memory. And by specifying all of these data types and knowing how many bytes they occupy, that allows you to have intimate knowledge and control of what's happening in memory. That's why this is such a big deal. Okay, we went through operators quickly. That's sort of what you've seen before. We did relational operators. Bitwise operations, we haven't seen that yet. That's important for embedded work. We'll start to see that next week. Okay, and then we blew through these control structures. Okay, so I'm going to go through the rest of these things now, just so that you've seen them. We're not going to do make here in this crash course. We'll wait until next week on that. So we'll say a little bit about arrays. We'll say a little bit more about functions, even though we've been seeing already. A little bit about scope and a little bit about pointers. Okay, arrays. You've seen arrays before, but array is a data structure where you can store a fixed size collection of elements of the same data type and with a common name. So for example, here I am declaring an array that has 5 elements in it. They're all floats, and they're all going to go by the name temp. And then I just typed in a bunch of, body temperatures, 98.6, 100.2, etc. So the syntax here shows you how you would initialize an array of 5 floats called temps for temperature. You put them in curly braces, you separate them by semicolon, by commas, all right? And it ends, like all C statements, it ends in a semicolon. The important thing here is that the array index goes from 0 to the array size -1. This is a place where people get tripped up. We usually think, if we have an array of 5 elements, we would access them as temp of 1, temp of 2, temp of 3, temp of 4, and temp of 5. In C, it goes temp 0, temp 1, temp 2, temp 3, and temp 4. Okay, so that's one thing that's particular to C. The other thing that's particular is that the way you access them, you don't use parentheses, but you use these square brackets. Okay. Another point is that when you are declaring an array, you can do it either way. You can specify how many elements are in the array, or you can choose not to. And the compiler will go and figure that out on its own while it's compiling the code. So you don't actually have to specify the size. It will figure it out for you by counting them. There are some deviations from that when you have, for example, what we call a multi-dimensional array, and I'll show you an example of that. Okay.
Professor, there's a question in the chat about initializing arrays.
Okay, go ahead. What's the question? Let's see.
To initialize an array, would you just do equals open curly brace, close curly brace?
So there are a number of ways of initializing the elements in an array. If you look at the way we're doing it here in this code, take a look at these first 2 lines where I am declaring and initializing the elements in the array. Alternatively, I could have just done this. I could do int. I'm trying to write with this mouse pen here, but int. Let's suppose I had a of 5. Suppose I just declared it like this, but I didn't initialize it. All right. So suppose that were my first line. Then I could go ahead and I could initialize the first one, a of 0. I would put it in a square brace, a of 0, equals, 12, whatever I want it to be. All right. And then a of 1 and so forth. I can't write with the mouse here. But there are different ways of initializing. Here in this example, we're initializing all the elements in the array at once, and we're doing that by putting them in curly brackets. Take a look at the output down here, just so you can see what this code is doing here. It's printing out age and temperature. So think, we're in a hospital and you've got a set of patients. And you're just printing out information, their age and what their temperature has to be. And I just wanted you to see how I've kind of got it nicely formatted there. I use some, if you look at the print statement here, right, you see all that structure in there. Let's break that down. Parenthesis B means print an int. /t means 2 tabs, so 2 tab stops. Parenthesis .2f is print a floating point with 2 significant figures. /end is print a carriage return. And so what you can see is we're looping through. I goes from 0, 1, 2, 3, and 4. And I'm just printing out ages of I and temps of I. Okay, so there's a simple example where we have a for loop and we're just looping through. Okay, how does the compiler know which int is being referred to? Well, in this particular, how does the compiler know which int is being referred to?
Professor, that question was answered in the chat a while ago.
Was, okay, all right.
My apologies.
Okay, I see. So I got a question. To initialize an array, could you just do brackets? No. So unlike MATLAB, in MATLAB, you can go ahead and you can process an entire array or matrix all at once, right? You can't do that here. Like you can't, let's say, define two arrays. Maybe they're both of the same type and the same size. Maybe you have A that has 5 elements and B that has 5 elements. You can't just say A equal B and have the expectation that it would get taken care of. It doesn't work that way. MATLAB allows you to do that. Not here. Here you have to actually index through and deal with all of them individually. So it's different from MATLAB that way. Okay. All right. Another example here. I just wanted to show you some text. So when you have a bunch of characters together, you call that a string, but a string is really just an array of characters. And so here I have a data type char for characters, and I created an array. I called it my string. I didn't specify the size. I'm going to let the compiler figure that out. And then I just defined it this way. And when you're dealing with an array of characters, you're allowed to put them in quotes to initialize them. So I've created a character array, and the contents of it are, wow, C is really a lot of fun. Okay. Take a look at the output down here. Okay. So it says, here is the string. Wow, C is really a lot of fun. It prints that. Then it says the string is 31 characters long. It prints it again, and then it's printing it backwards. And the first time it prints it backwards, it's sort of missing the first character, the W. And then the second time we print it backward, we're getting it correctly. So I just wanted you to see a little bit about that. How do you find out the length of a string? There's a library function called strlen, short for string length. That library function has its prototype or its declaration here in this header file string. We've been using include stdio.h in every program we've done, because that defines printf for us. Here I want to use the function strlen. That's a library function. And so by including string.h, that allows me to use that library function. And so here I just used it in this line here. Here is the string. I printed it out. And then I said, the string is so many characters long. And I just used I had computed length, and then I printed out length here. Okay, in this for loop, I'm just printing out the contents of that array, one character at a time. I'm going from 0 up to 1 minus length, right? And I'm just printing them out one character at a time. Here, I just did the same thing, but I went backward. And I went from length down to 1, and I decremented here. I minus minus is I equals I minus 1. And when we did it this way, what happened is we missed the very first character in the array. And that's because the index of the first character is 0. And so in the condition here is I greater than 0. That actually missed the 0th character. So we got it correct in this one by doing I greater than or equal to 0. Okay, so that's a little bit about strings. Okay, the next one, here I have it's actually a 2-dimensional array. What I wanted to do is it's an array of strings. So I actually have, I defined an array where the first element of the array is the string called red, the colors of the rainbow. The second one is orange, green, yellow, and so forth. Let's just look at the output down here. All right, it just printed those colors, right? Red, orange, yellow, green, blue, indigo, and violet. The only thing here that's kind of peculiar is the way we specify a 2-dimensional array here. So the first dimension is the actual number of elements. We have 1, 2, 3, 4, 5, 6, and 7. And I didn't have to specify that. The compiler figured it out. Okay, but one of the kind of the quirks of C or highlights of C is that when you do have a multi-dimensional array, you have to specify the maximum length of the second dimension. So I had to specify that the maximum length of these would be 10 characters. If I need you to know more about this, I'll let you know. We'll spend the time to get you comfortable with this. So if this is seeming to be confusing for you right now, don't worry about it too much. We're not going to do a whole lot with character strings because microcontrollers don't have they don't have a head. They don't have a monitor with them. We will be dealing a little bit with one of these tiny organic LED displays, and we'll be sending some characters to that. And when it's important for us to dig into this, we'll spend some time making sure everyone's comfortable with it. Okay. I want to just say a little bit about the homework assignment that you're working on. Make sure you sort of have an algorithmic approach for doing it. And so how do you convert a number from base 10 to binary? Let's say an integer in base 10, how do you convert it to binary? Let's look at the example on the right. So 15 in base 10 is 00001111. And you know what I want to do here? What I'm doing here is I'm sort of building up an algorithm that you can use to solve the homework assignment. Before I do that, let me just go and show you what the typical output for the homework assignment would look like. So I'm going to go to the next slide here, slide 10. Okay, here's what it is. This is what sort of sample IO. Okay, so I run it and it says, okay, please enter a number in a base separated by a space. And I typed in 127 and 10. So it tells me 127 in base 10 is 127. All right, I'm looping through. I'm going to keep looping until the user enters 0 and 0. So I specify 127 and 8. It says 127 in base 8 is 177. All right, 127 and 16. It says 127 in base 16 is 7F. Now, so far, all I'm doing is using, I have an if statement, an if statement. And I'm just using printf with format specifiers for decimal, octal, and hexadecimal. That is parenthesis D, parenthesis O, or parenthesis X. So it's easy. You get these things for free. The next one is the one where you had to work a little bit. If I entered 127 and 2, it means I want to see 127 in base 2. So I had to create a function that's going to go and get this and print it out for me. I also said 127 and 5. All right, we're not interested in base 5. So we told, I printed out the instruction, please enter a base of either 16, 10, 8, or 2. Okay, then I did 2, 2, and I got 2 in base 2. Then I typed in 0, and it waited, and then I had to type in another 0 before it finally stopped because I've got a scanf that's looking for 2 numbers. Okay. So the input values here should be ints between 1 and 255. That's the specification for the problem. Okay, just want to clarify that they should be ints. And you only have to work with numbers up to 255 so that you're only dealing with 8 bits. You could go beyond that, but we keep it simple by keeping it to 8 bits. So what's an algorithm? How do we take something like 127 and how do we convert that to binary here? I'll go back to slide 9. Okay.
Professor, we have a question.
Go ahead.
For the output of binary numbers, like for the 15, would we have to output the 4 zeros in the front, or could I just output 1111?
Since I didn't specify that in the problem statement, you're okay with just specifying 1111 and not having the leading zeros. I would prefer that you have the leading zeros, but a number of you have already submitted this code, and it's unfair for me to add this as a requirement on right now. Okay, so there's your answer. You're okay with not printing the leading zeros. That having been said, one of the purposes of this is to get you comfortable manipulating ones and zeros. And we're really going to get serious about this a week from today. We'll be way down in the thick of this, doing all kinds of called bit twiddling, bit level manipulations. So while you don't have to worry about those leading zeros for the assignment, if you got some time, you may want to try to figure it out. Okay, fair enough. Okay.
I think we have another question.
Yep.
Is it necessary for us to comment our code?
Are they required to put comments in their code?
Yes, always put comments. At least put a block comment. At least put a block comment on top. Your name and a little bit about what it does, and then it's good practice to have some inline comments down below. Use your discretion on there, but I want at least a block comment up at the top. Okay, and then when we get to the point where I want more than that, I'll be more explicit in the assignment. Okay. Okay, I've got a question. Can the project contain every base function in one main function, or do I want separate functions for base 2, 10, and 16 to be separate from main? Well, I did in the specification, I instructed you to use a function to handle the base conversion. So you can interpret that lots of ways. What I would encourage you to do is just use printf to handle the conversion between decimal and base 2, 10, and 8. So you don't have to do any work for that. Then when you want to convert to base 2, I would encourage you to put that into a function. If on the other hand, you want to do it differently, that's okay. But I think from a programming style point of view, since getting the results in base 10, 16, and 8 is trivial with a print statement, it makes sense to keep all that up in main. And then the part that you have to do some thinking, which is on this slide, that's the kind of thing that you should tuck away in a function.
We have another question in the room.
Go ahead.
Yeah, you just want us to submit the C file, right?
I want the C file, and I also want this screen capture.
That's screen capture. Okay.
So those two things, yeah. Show me the C code and then the screen capture. Okay. All right. Just how do we do this? I mean, it's pretty simple. Take the number 15. If we divide it by 2, right, integer division, it's 7 remainder 1. How do we get the remainder? 15 modulo 1 is 1, and that's our least significant bit. And you just keep repeating that. You do that whole thing 8 times. Do that 8 times, and you're going to get your least significant bit on up to your most significant bit. Okay. It applies whether it's a small number like 15 or a big number like 256. You just keep dividing it, and you're going to divide it, 1, 2, 3, 4, 5, 6, 7, 8 times, and it's the result of this. You're dividing it by 2, and then it's the result of the modulo 2 that gives you your bits, be they 1 or 0. Okay, and so there's the algorithm down there. I mean, I'm not giving you the code, but I wanted to just give you a start on how to do it. And I'm aware that some of you are already seeking help from the TAs on this, and that's fine. Okay, all right. At this point, we're sort of close to wrapping up this whole crash course on C. I just wanted to revisit the idea of a function. And when we first started, the very first exposure to C, I showed you int main void, like this line down here, and everyone is like, what is int? What is void? What is this function? What does all this mean, right? Well, by this point, you know what int means. You know what these variable types are. So let's just think a little bit more about a function, right? Some people ask, what's the difference between C and C++? If you were to Google, if you go to the computer science language and ask them to define, C, they'll tell you that C is a procedural language. Okay, what's a procedure? A procedure is a recipe, right? You want to do something, you do it this way, right? You want to bake a cake, you get the bread, you mix the flour and the eggs, stir it all up, right? That's a recipe, right? So it's a language that's really based on procedures or functions or recipes, right? So it's a language that you can think about it where the building blocks are these functions, which are procedures. And all functions have this same basic sort of structure to them, the header, right? There's the name of the function, okay? Then when you call the function, you're going to give it some arguments. You're passing some stuff, some arguments to the function. And then when the function's done, it will return a variable of a certain type. So when you characterize a function, you need to know what's its name, what are the arguments that are being passed to it, and what's its return type. And let's look at this example. Suppose I tell you I have a function that's going to return the square of a number. Okay, and the input and the output are floats, right? This tells you everything you need to know to use this function. This function returns the square of a number. The input and the output are floats. So you call it up, right, by invoking the name square. You'll give it a float and you'll get back a float. And what you get back is the square of the input. And so here is an example of a main function that could make use of it. Now, this is kind of a very simple example, right? But so what are we doing here? I'm starting out, I'm defining a couple of variables, n and n squared. I'm saying n equals 5.0. NSQ is square of n. So I'm calling this function square, and I know I'm going to get back the square of n, okay? And then I'm just printing out the square, and then I'm done, all right? Now, over here on the right, I'm showing 3 different ways you could implement this function. You could implement the function in lots of different ways, right? I mean, it's a simple function, so all it's doing is giving you the square of something. But look at this first one, right? I chose some variable names, right? I chose num and num squared, right? And you can see what it's going to do is it's receiving this value here. Within the function square, I'm declaring a value num squared, which is the product of num times itself, and I return num squared. Okay, and I've done what the header has promised. I've accepted a float, and I've returned a float that is the square of the argument that was sent to me. Right? Here's another implementation, and there's another implementation. Right? So the point about functions is you can implement them in lots of different ways. How it's actually implemented is not important from the point of view of main. Main just has to know what's the function header, what's it returning, and what type do I have to give it, and what's it going to do. Okay, so I want to talk about it. Go ahead.
There's a question in the chat. I assume you could have something like int bracket 2 function name if you wanted to return 2 integers in an array.
Okay, let's see. I assume you could have something like int2. No. That wouldn't work. I'm going to show you at the end how you can return 2 integers. It wouldn't work like that. But return is just going to return one thing. But I'm going to show you how it is that you can return multiple things from a function. Okay, using pointers. Okay, I want to say a little bit about variable scope. All right, this is an important concept, and scope is where variables are visible. Okay, and so let's look here. I have 2 different implementations of float. All right, I have this one here where I've chosen certain names of variables, n and n squared, and here I've just chosen some gibberish. Right, I've just chosen to implement it using various. Those are not legal variable names, but I just wanted to illustrate the point that when you design a function, you can implement it internally any way you want. Okay. Now I want to talk about where these different variables are visible. So over in main, okay, over here, the variables that we have are num sq. That's it, right? And those variables are local to main. They're only visible in main. So the function square doesn't know anything about those variables. They're local to main. Conversely, if you look at this function up here, it has its own local variable space. It has n and n squared. Those are local to square. Those variables are only visible to that function square. And then in this crazy one down here, however it's done, you know, the variables it uses are local to it. So there's this point about the scope here is that all of the variables we're dealing with here are local variables. It's almost like, it's almost like when you design a function, right? How you actually do it is nobody else's business. It's not the business of main to get into and care about the implementation of the function square. All that matters is the function header that tells main everything you need to know, right? Float, square, float. We call it with the name square. We pass the value of a float, and it'll return a float, and it's going to go ahead and square it for us. But the implementation and the variables being used by the function are invisible to main. Okay, so now, so that's this idea of scope. How is it actually done? How does all this work? Well, if the variable structure in the function square is unknown to the variable structure in main, how does it work? The answer is pass by value. You actually, when we invoke square, right? If we call square over here in main, right, with this line here, what it's doing is it's taking the value of num, which happens to be 5, and is putting 5 over here. It's sending just the value itself, 5, into function square. So function square doesn't know num, it doesn't know anything else about main other than it's receiving the value 5. Okay, so what you're doing is you're not passing the variable, you're not passing the memory location of that variable, you're just passing the value of that variable. So the function square gets that value 5. It does its number crunching and it's sending back the value 25. And then we make use of it over here. So we're only passing values between these functions. We're not passing variables. We're not passing variable addresses unless we take pains to do that, right? We're just passing by value, right? And the reason why this is done is the whole philosophy here is divide and conquer. That is, you need to get something done in a function, go off and do it, implement it any way you want. You can be guaranteed that that function will not interact with main or the other functions except as specified in the header. Okay, so how do we pass back more than one thing, right? That was a question that was asked. How do we return more than one thing? Well, I'm going to get to that, but I want to just expand on this notion of scope a little bit more. All right, so scope, where a variable is visible. Okay, and we just talked about this local scope. If you have variables that are declared within a function, they're only visible within that function itself. But you also have something called global scope. You can declare a value if you choose to outside of a function. And that in that case, it will be visible within all of the functions that are in the file. And I'm going to show you an example of that. All right. Now this is getting a little complicated, this particular piece of code here. But I wrote this to just demonstrate a global variable. Okay, first of all, let's take a look at the output. Okay, it's not taking any input. It just says you are 59 years old and you were born in 1963. You're 71,000 something days old. Now you're 60 years old. Okay. Now let's look at the structure here. Okay. I have let's look at main here first, and then we'll look at everything else. Okay. I have a local variable called age in days. All right. A print statement. You are so many years old and you were born in something else. Okay. What's the first thing that gets printed? Age in years. Where is age in years defined? It's defined up here. It's defined before I actually had the header for main. So it's defined outside of main. That makes it a global variable. So age in years is a global variable. It's visible, it's accessible to all the functions in this file. That's different from if I had defined that within main, it would only be visible within main. And so the whole point behind this whole program is I have a function down here that is modifying age in years, right? It's actually taking age in years and increasing it. And that is causing a change in the variable age in years throughout the entire file. So what's actually happening up here is in the first part of this, it's printing out you're 59 years old, and this is, that's how many days old you are. Then it actually calls this function called a year older. That function increases the value of that global variable and then prints it out. I know I've gone through that about 5 times faster than I would need to for you to really understand it all, but I just wanted you to see an example of a global variable that's visible to all the functions in the file. Okay, all right, and then the very last thing I wanted to show you here in this crash course is a pointer. Here's an interesting statement here at tutorialspoint.com. It says pointers in C are easy and fun to learn. They are not easy and they are not fun to learn. But let's be optimistic. Think about the function scanf, right? Which we've been looking at already, right? We've been dealing with this for a while, and we know I would need a semicolon here, right? We know what this function is going to do. It's going to get from the keyboard an int, and it's going to store that in variable input 1. And then it'll get another int, and it'll store that in variable input 2. So after this statement is executed, the value of input 1 has been changed by this function. Now, how did that happen, given what we just talked about with scope and everything else, right? How is it that input 1, the actual contents of the variable input 1, how are they modified by scanf? Given that we just talked about functions pass by value, right? You don't actually pass the variable from main into the function. You're passing the contents of that variable. So how does scanf know to go in and change the value of variable input 1? The key is this ampersand here. That's the address of operator. Okay. So when we do this, we're specifying the memory addresses of variables input 1 and input 2. So when we call f, we're telling it, go to the memory location associated with variable input 1 and stick something in there. Put an int in there. Likewise, go to the memory location associated with input 2 and put another int there. So when you preface the variable with this ampersand, you've created what's called a pointer. It's no longer the variable input 1, but it's the memory location associated with variable input 1. And that's how scanf is working. What scanf is doing is it's causing the user's input, according to the modifier D, to be placed at memory location corresponding to input 1. That's a pointer. Okay. And there are some key points here. This is a tricky thing to get your head around the first time you see it. So I'm not going to elaborate on it here. I just wanted you to sort of see it again. It's when you have ampersand A, that refers to the memory contents of A. And if you have asterisk P, then you're sort of declaring a pointer, and you're referring to the contents of memory address P. I'm not going to say more about pointers right now. When we do have occasion to sort of see this in more detail, we'll spend time on it next week. Okay. And with that, here I've got an example of some code here that makes use of pointers to swap some variables in a function. It's tricky. It's hard to get your mind around this when you first start to see it. Don't worry about it for right now. Just hear the words pointer and this notion of address of. And you know what, folks? We got 1 minute left of class, and we've finished this crash course on C already with 1 minute to spare. We're still working on the kits. We've got a little over 100 of them made out of 300. I'm going to let you know when you can pick them up as soon as we can. You won't actually start to do anything with the contents of the kits until Wednesday, a week from today.